Yeah, let's look at this topic in mathematics, circle geometry. Then we need to know some part of a circle. First, let's define a circle. What is a circle? Circle can be defined as locus of points equidistant from a fixed point. Locus of point which is equidistant from a fixed point. Now let's consider here how we mean by this. We have a fixed point O, then with equal distance. This distance is r. So this locus moving with this distance, equal distance from this fixed point. This is referred to as a circle. The locus of a point equidistant from a fixed point. Right, now let's consider some parts of circle. The first part of circle we should be able to identify is circumference. We have circumference. 2, we have radius. 3, we have diameter. 4, we have chord. 5, we have arc. 6, we have sector. 7, we have segment. Now let's consider this circle, which is center O. What is the circumference here? Circumference is the distance around the circle. This movement around the circle is what is called circumference. That's the first part of a circle that we should be familiar with as far as circle theorem is concerned. And also, what is radius? Radius is a line drawn from the center of the circle to the part of circumference. Like when we draw a line from here, this line drawn from the center to the part of circumference here is called a radius. Okay? So that's a radius. It could be to any part. Once it is from the center to the part of circumference, like from the center here, it's also a radius. So that is that. All right. Now, what is a diameter? A diameter pass through the center of the circle. Pass through the center of the circle and touch the circumference at both sides. So if we extend this line drawn and it's passing through the center to this side, of course, this line that touch the circumference at both sides and pass through the center is called diameter. And from the center to this circumference is also a radius. So we can see diameter as radius plus radius. So diameter D is equals to 2r. So that is that. And also, what is a chord? A chord is any part of the circumference. Sorry, a chord is a line that touches circumference rather at any 2 points. So if you draw a line that touches circumference here, this line that touches circumference at 2 points here is called a chord. So this is a chord, and which implies that diameter is also a chord because it also touches the circumference at two sides. And therefore, diameter is referred to as the longest chord of any circle. The longest chord of any. You have a circle, and you have the center, and you have a line drawn this way that touches circumference at both sides. So this line is what is referred to as a chord. So this is a chord. And also we have an arc. An arc is any part of the circumference. Cut any part of the circumference out. For instance, from this point to this point now, We label this as A and this as B. So this part AB is an arc, like we cut it an arc. And if we cut this one out, it's smaller than the other one. So this can be referred to as the minor, and the other one that is the bigger one be referred to as the major arc. So that is an arc. And what about sector? A sector is a region that is bounded by two radii and an arc. So for sector, we have two radii and we have an arc. So let's see from here. We have these two radii here, and we have this arc. So this region that is bounded by these two radii, which is BO and AB. So, and this arc AB. So this region is what is called sector. The other one unshaded, if we clean all this line, the other one also bounded by this arc and this radius, two radius, is also a sector. This one shaded will be a minor sector and the other one is a major sector. So that's a sector. How about a segment? A segment is a region bounded by a chord and an arc. We have a chord and an arc, like this chord now. If this is chord AB, surrounded by this chord and this arc AB as well. So this region is what is called segment. So we have segment. The one shaded here is the minor segment, while the one unshaded here is also a segment. It's also bounded by this chord and this arc. So that one is a major segment. So these are the part of the circle we should be familiar with before we go to circle theory. Now let's consider some lemma first. We should have the understanding that a chord or an arc can subtend an angle at the center of a circle. So number one, we have a circle center O with a chord and label it as AB, or it might be an arc. You have a circle center O with an arc AB. So this chord or this arc subtends two angles at the center. By the word subtends here, it means form. So the word subtend, same thing as the word form. So this chord form angle at the center. So when we connect A to O and also B to O, so we have two angles at the center here. So this angle inside, which is interior angle, and we can call it the obtuse angle AOB. By obtuse angle, it means angle that is less than 180 degree but greater than 90 degree. So this angle here, this angle is center. The other one too, which is the opposite angle here, which is the reflex angle greater than 180 degree. So that's angle AOB, reflex angle AOB. So a chord subtends two angle at center. Likewise, an arc. We have an arc here. This arc forms this angle here. Also, the one inside and the one outside. So that is the first thing that we should understand here. Then also we have a chord also form angle at the circumference. of a circle. So if you have a circle this way with center O, and we have a chord AB, or it might be an arc. So we have a circle also with center O, and in this case it might be an arc AB. So this chord form angle at the circumference in the major segment here, also form another angle in the minor segment here. So we have two angles at circumference as well. One angle here we can label it as C and this as D. So you can say one, we have angle ACB at the circumference there, or two, we have angle ADB at the circumference. Similarly here, it might be an arc. This arc also form this angle at the circumference at this part. And label it as C as well, and also form this angle at the other side, and we can label this as D. So having the understanding of this will make the theorem to be easier for us. Now let's consider the first theorem in circle. So we label this as the theorem 1. And the theorem 1 states that the angle subtended by a chord or arc at the center of a circle is twice that which it's subtended or subtended at the circumference of the circle. So this theorem is very important as far as circle theorem is concerned, and the ability to be able to prove the theorem will go a long way in helping us to solve problem that is relating to it. Now let's look at the proof of this theorem. From the theorem, we have the angle subtended by a chord or an arc at the center of a circle. First thing, we should list what you are given. We can say given, we are given first a circle center O. So we can draw the diagram as we state it, we describe it, we represent it. So we have a circle center O. Now, this given we are listing, we are not picking it up and we're only looking at the theorem and we are extracting it. Now, the angle subtended by a chord or arc at the center of a circle, that means we must have a circle. Now, we have a chord or an arc. So we can say, let's use a chord here. We have chord AB, given chord AB. So we can draw the chord as we want it. So this is a chord AB. Then, next thing we are given is we have an angle there, and we say that angle is at the center. The angle at the center formed by the chord. So we form an angle by the chord at the center here. So we have this angle formed at the center here. So we can say the next thing we have here is angle AOB, which is obtuse. Obtuse angle AOB at the center. We consider this obtuse angle less than 180 degree. Now, also is twice that which is obtained as circumference. We also have angle as circumference. That's number 4. We have angle. We can form the angle as circumference, and we write it out. Here we have, anywhere you form it, just make sure it's at the circumference. So we have this angle as circumference. You can call this angle C, which is this angle. So angle ACB at circumference. So these are what we are given. Now, the next thing is required. What are we required to prove from the theorem? We have to prove that angle at the center, which is to prove that angle at the center, we are going to write it using letter now, which is angle, to prove that angle AOB is equals to 2 times angle at the circumference, which is angle ACB. So that's all we are proving. Just pay attention and see how this is proved. It's actually simple and direct. Now, after required, there is something called construction. So we do construction here. Join C to O and extend to a letter D. So by the construction here, we join this point C to point O and we extend it to maybe letter D here. Now, going to the proof now, from what we have, this line, this construction line has divided this shape into 2 triangles. And considering triangle AOC, from triangle AOC, looking at this side, we have AOC. We discover that line AO will be the same thing as line CO. Why are they the same thing? Because both are radii or semicircle. Look at it. AO is from the center to the circumference. CO is also from the center to the circumference. So both are radii. Then we can say that this triangle AOC is an isosceles triangle. That's the property of an isosceles triangle. 2 sides are equal. And we can therefore establish that base angle are equal as well, which implies that angle ACO, this angle, is same thing as angle CAO, this angle, and we can label it as letter X. So since this angle are equal, we call this letter X and we call this letter X. And therefore, one side of this triangle is extended. This side is extended, which is exterior angle, which can be labeled as AOD. So we say angle AOD is extended. Exterior angle is equal to sum of the 2 opposite interior angle. That's X plus X, which is 2X. That's exterior angle of a triangle. So if this is 2X now, similarly, we do the same thing for the other triangle here, which is BOC. So we can say similarly, triangle BOC is also an isosceles triangle. Why? Because we have 2 sides equal. BO is equals to CO. Both are also radii or semicircle. And the base angle are also equal. This is the base angle here now. That is, here, this angle and this angle, will also be the same thing. So we label this as y and this as y. Okay, because of space, let's just put it in diagram here. And also exterior angle here will also be equal of the opposite interior angle. You can say y plus y. This is 2y. So in conclusion now, let's conclude now. Conclusion. Now, we discover that angle AOB, which is angle at the center, the entire angle at the center here is adding up to 2x plus 2y. So that is it, the angle at the center. And here, 2 is common. We can say angle AOB is now equals to 2 into bracket x plus y. Now, but angle at circumference ACB is same thing as x plus y. When you look at it, the entire angle at circumference here, ACB, is x plus y. So we want to remove this x plus y and now write angle ACB. So we can say angle AOB is now equals to 2 multiplied by angle ACB. That means the required has been proved. Therefore, we conclude that angle at the center is equals to 2 times angle at the center. Now, briefly, in essence, what we are saying is that if we have a circle this way and we have this center of the circle and an angle is formed whether by an arc here labeled as arc AB or chord AB, whichever one. Angle at center will be double or twice that of angle at circumference. So if we have another angle at the circumference here and the angle at circumference here is maybe 20, for instance, angle at center now will now be 2 times 20, which is now 40. So that is in essence what you are talking about as far as circle theorem is concerned. All right, I believe you are enjoying this class. Why not subscribe and share this video and also give your thumbs up, and thank you for connecting. Now, let's look at one direct question here, which is application of this theorem. So you can say we have from here example. We have a circle, center hole, and we are given this line here labeled as A, B here. Of course, this center and an angle is formed at the circumference here, which is labeled as C. So this is labeled as C at the circumference. Okay, sorry. We have this here. This point is point C, and this angle is labeled as 26 degrees. This angle is labeled as 130 degrees. And they put a line here, like a construction line here. And if that line is not being put there, when we are solving a question by ourselves, we should see that there will be need for that. And the question says, find one, angle CBO, and 2, angle BOC. Now, where is angle CBO? We should know where we are going in order to know how we're going to get there. So, angle CBO, this angle is what we are finding for the first one. Then angle BOC, this angle is the other angle we are finding, which is the two questions asked. Now, let's consider what we have here. We have angle at center AOB to be 130 degree. And from the theorem we looked at, this angle which is at center is double that angle at circumference, which is angle ACB. So in other words, we can find angle ACB. Since you know the angle at the center, angle at circumference ACB will now be 130 degrees over 2, which will be 65 degrees. That is, the whole of this angle at the circumference now is 65 degrees. But now, consider from triangle AOC here. On triangle AOC, line AO is equals to line CO. Both are radar. So that means that triangle is an isosceles triangle, which makes this triangle an isosceles triangle. So we can say the base angle here will be equal. This angle is 26. This angle, which is the base, also is 26 degrees. That is, when we write it as angle ACO will be equals to 26 degrees as well. That's base angle of isosceles triangle. Now, don't forget that the whole of this angle is 65 degrees, and we got this to be 26 degrees. Now, we can get this angle now by subtracting 26 from 65. And this angle marked here, using 3 letters, is angle BCO. So, angle BCO is then equals to 65 degrees minus 26 degrees, which is equals to 39 degrees. Now, we got this angle to be 39 degrees. We can equally get this angle. Similarly, that is base angle of isosceles triangle, which means this angle you are finding, which is CBO, that's the first one. Therefore, angle CBO is also equals to 39 degrees. You put the reason why base angle of isosceles triangle BOC. Then, the second question here, we got this one to be 39 now, and we are finding this angle BOC, and that angle BOC completes this triangle, because we have 3 angles here now, and sum of angle in a triangle should be 180 degrees. So that will now be 180 degrees minus 39 plus 39, and that gives us 78 degrees. So 180 minus 78 degrees, that's got 102 degrees. So this here we have the solution to this problem. It was easier to solve. Why? Because of the first theorem that we already know. All right. So share this video, give a thumbs up, and subscribe as well. Thank you for connecting. Now we also have theorem 2, and from theorem 2, what we have there is the angle subtended or subtended by a chord or an arc of a circle in the same segment are equal. So let's quickly look at it and see the proof of that theorem. So let's label this as theorem 2 here. We have the angle subtended by a chord or an arc of a circle in the same segments. In the same segments are equal. So let's say the angles, because not one angle. So that's theorem number 2. The angles subtended by a chord or an arc of a circle in the same segment are all equal. Are all equal. So all those angles are equal. Let's look at it. We have a circle. Let's just look at the drawing and see the proof. So we given on the proof, we are going to be given a circle which is center hole, and is it that we have a chord or an arc? But in this case, we can still make use of a chord. So we can say we have a chord. This is a chord. We can label it as AB. And now, what this theorem is saying is that the angle formed by this chord in one segment, because now this chord here has divided this circle into 2 segments. We have this segment up here and we have the one down here. This one down here is the minor segment and the one up is the major segment. Now, if we form angle by this chord in one segment like this, we have this angle now forming by this chord in this part of the circle, in this segment. So this angle here, now we can still form another one. Here. It's not necessarily we have one angle. So this chord is still forming the angle, but say in this segment at the circumference, making 2 now, we can still form another one by this chord AB, making 3 now. It might be more than 3. Now, what this theorem is saying is that all these angles are equal. And the theorem follows from theorem 1. So, let's see why they are equal. By construction, we join A to O and also B to O. So, join this to the center. We have the angle at center here now. Don't forget, the angle at center is twice the angle at circumference. Assuming we know one of these angles, let's say one of these angles is x. What will be the angle at the center? Because angle at center is twice the angle at circumference. So this angle will be 2x. And when you look at this angle critically, it's also at the circumference. Why this angle is at the center? So if this angle 2x is at the center, angle at circumference 2 here will be x. This is 2x, this also will be x. So automatically all these angles are equal. So that is the proof of the theorem. It's directly from the first theorem. So which implies that angle in the same segment are equal. So you can just say angle in the same segment are equal. So we need to master all this theorem in order to solve problem easily under circle. Like for instance, we can consider this question here. Something like this is just drawn. We have this. Now, merely looking at this now, we put one angle here, one angle here. We have 40 degrees here. We have y here. And they said find the value of y. When you look at it critically, this 40 and y, they are in the same segment. You ask why? Because when you look at it from this angle, on this side, when we label it as AB, this is an arc now, which subtends this angle y as circumference, also subtending this angle 40 as circumference. So these two angles now lies in the same segment of the circle. So that therefore we say y here is equals to 40 degree. Why? Why is it 40 degree? Angle in the same segment. Like for instance as well, you might say this is x and this is 35 degrees. So without mixing word, we say x also is 35 degrees. Why is it so? Because looking at it from this other angle, other side, if this is C, this is D, we discover that this chord CD subtend this angle at the circumference here, also subtend this angle at circumference here. So both angle here lies in the same segment. So therefore, x equals 35 degree, angle in the same segment. So let's understand this theorem, these two theorems. As we are building on it gradually, we'll be able to solve more complex solutions as far as circle theorem is concerned. If you are a student sitting for an external examination like this, class is meant for you. And if you know anyone, you can just share this video to them, so it will be of help in their examination, and so that whenever we meet, we go live, we have access to it. So just subscribe, turn the notification bell, and share this video as well. Now we have another theorem here, number 3 theorem, and that theorem also has its proofs. Its proof from the first theorem. So let's call this theorem 3 here. And the theorem states that angle subtended or subtended by a diameter at the circumference is 90 degrees. The angle subtended, the angle subtended by a diameter at the circumference. At the circumference is 90 degree right angle. Or we can say angle in a semicircle. In a semicircle is right angle. When you hear right angle, that's angle 90 degree. Angle in a semicircle is angle 90 degree. Now, the two mean the same thing. We have a circle which is center hole here, and we have a diameter. A diameter passed through the center of a circle. We can label it as AB. And the interesting thing here is that this diameter has cut this circle into two equal halves. That's why we say semicircle. Semi means half. So we have half of a circle now. And for this, we have a circle, and for this angle subtended by this diameter at one part of this circumference, at any part of the circumference, that angle is 90 degrees. Let's form an angle here now by this diameter. So this angle formed is angle 90 degrees. The proof is simple and direct from the theorem 1, which says angle at center is twice angle at circumference. We label it as C. So angle at center AOB here. What is the angle at center here? AOB. Now you have a straight line. Straight line angle, that's 180 degrees. So this angle is 180 degrees. And this is at the circumference. And you know that angle at center is bigger than the angle at circumference. So it's twice the angle at circumference. So if we don't know this angle at circumference before, we just divide this one by 2. So we can say that angle ACB will now be equals to 180 degrees over 2, which is automatically 90 degrees. So that is why whenever we have angle by a diameter at the circumference, that angle is automatically 90 degrees. And this is a symbol for 90 degrees, like a square, 4 corner. So you don't need to write this sometimes. You just see that symbol. You already know that the angle is 90 degrees. All right. So we have that as theorem number 3. Okay, that's theorem 3 for this class. All right. So also there are other theorems as well. This one is theorem 3 here. We have looked at 3 theorems now. So the application of this theorem as well is very important. Very important. You are familiar with it. Okay, so let's continue from here in our next class. Don't forget to subscribe and turn the notification bell on. And when next we meet, continue. See you in our next class. And bye for now.